Hello, I'm Tommy Lau Wu. Now I would like to demonstrate my MC13 project, which using the EDA Playground to design and simulate the different digital system modules. And inside this project, we have 3 questions, and each question has the respective module required to be simulated and also verified. And also, some of the modules we need to design and verify for its functionality. Without further ado, let us start for the question 1. For the question 1, I simulate a module for the half-adder HA, which design in data flow coding style, where the S equal to A S O B and C equal to A and B. A simple testbench is created, which sending all possible cases for the input A and B to the half-adder, and the output F and C will expect to generate during inside the waveform. Run the simulation. As we can see, the C and S are generated as expected behavior, then which means the half adder is correctly simulated. Next is the full adder. We have 2 syntax for the full adder that using same coding style with the structural coding style. But for the full adder version 2, it is using the positional connection, port connection syntax, while the full adder version 3 is using the naming port connection syntax. Inside the full adder, they are using 2 half adder blocks to realize the full adder behavior. Then we create a test bench to verify the full adder. Since the full adder version 2 and version 3 are similar, so we just simulate the full adder version 3 by sending different possible cases of the inputs A, B, and C in. Let's run the simulation. As we can see from the simulation, for each possible case, the CL and sum also sending out all correct and expected output waveform. So this means the full adder is correctly simulated. Okay, next is the RCA 4 with the 4-bit Reaper carry adder, which designed using the structural coding style by integrating 4 full adder blocks together. And we have another test bench for the RCA4 with sending also different cases for the inputs A, B, and C in. Then we run the simulation. As we can see here, the sum will be the sum of the A, B, and C in, while the C out will be exerted if the value of sum is overflow. For example, for the first case, we add 5, 7, and C in is 0, it will get the result 12. Since the value 12 is not overflow, so C in, C out is 0. For another example, we add 7 and 9, while C in is 0, so actually it will added and the result will be 16. The 16 is overflow in sum, 4-bit sum, so the CR will be set to 1, while the sum will be the remainder, or which is 16 minus 16 will be 0. And so on. The cases are generated expected output, so the Reaper carry adder is correctly designed. Okay, next we also design an 8-bit Reaper carry adder by integrating 2 4-bit Reaper carry adder module together, and we test it by sending different value of A, B, and choosing either sub is addition or subtraction. Subtraction means that the sub will be equal to 1, while addition, the sub will be tai low. Then we run the simulation. And from the waveform, for the first case, the sub is 0, which means we do addition, A plus B. 90x plus 17, we will get a 150, which is expected. While for the next case, we assert the sub. such signal, which means we do subtraction A minus B. 121 minus 54, we will get a 67, which is correct as expected. And let us choose another case. For example, 68 plus 199, where the start is 0, and we will get a 11. This and C out is 1, which means that the C out, the value is overflow, because 199 plus 68 it actually is 267, which is actually overflow the maximum value of the sum, which is 255. So it will print out the remainder 11 and insert the C out. 11 is we can get from 267 minus 256, and we will get 11. And we can say that the FA ripple calculator is correctly designed and simulated. Okay, for question 2, I will simulate a block named BCD77 decoder, which will decode the input BCD to its respective LED value or pattern. For each case of the BCD, the LED will set to different value and pattern so that the value of the BCD will be printed out correctly at the 77 display later. And this is a simple testbench which run together with the BCD77 decoder during the simulation. Let's run the simulation. Then we can see here for each case of the BCD input, the LED will display different values based on the BCD value. This means that the BCD77 decoder can be simulated. Next, we design for the DPU unit, DPU or data path unit, which will do some arithmetic operation. For example, or SO, N, minus, and plus for the A in and B in. And for the data path unit, we also have a debug interface which will print out the values, internal wires or internal values that we need for debug purpose. Then for the output, we will connect to a BCD7 decoder to decode the output of the arithmetic operation to the pattern that we need to display at the 77 display. Then the operation will be controlled by ALUOP, which means when the operation is 0, the output will display the A in. When it's 1, it will all A in and B in. When the operation is 2, it will do SO. When 3, it will do N binary and BYS N. And also when its operation is 4, it will do subtraction A minus B in. And 5, it will do addition of A in and B in. Else it will display the B in value. Attachment will be also created to verify the data path unit to check whether the data path unit can cover all the possible cases that we set inside the testbench. As you can see, we will set the ALUOP to all 6 cases 0, 1, 2, 3, 4, 5, while the A in and B in will set to this value is 5 and B in is 2. And the deselect will be select whether the debug signal display at the D out output signal. Let's run the simulation. As we can see here, the D in will be including the ALUOP, A in and B in. So we can see as here. For example, A in is 5, B in is 2, while the ALUOP will be 4 bit ahead, which means it's 0 initially. 125 means ALUOP is 1. Yeah, 225 will be ALUOP equal to 2, and so on. And the D out will be displaying the debug signal according to the deselect. Deselect equal to 2 means D out will display the output from the arithmetic operation, which when ALUOP is 0, will be displaying out the A in, which is 5. When it's 1, it will doing the S or BYS O between A in and B, while 2 is the SO between A and B, and so on. And all the values are expected So this means that the data path unit is correctly designed. And the segment will display all the correct value based on the result from the ALU operation. Next, for the question 3. Firstly, we simulate a M1 module, which actually is a out counter, which will select the different step by using the selector signal. When selector is 0, the counter will increment by in1, and while selector is 1, the counter will increment by in1 plus in2, and when selector is 2, the counter will increment by in2. And when each of the process of the clock, the output will be increment by the values that we select before. Then a testbench is created by setting in1 to 2, in2 to 3, and the initially selector is select equal to 0. Then we wait until the output increment until greater than 5. We change the select to 1. And then we wait until output is 15. Then we change the select to 2 until the output is greater than 35. We finish the operation. Let's start the simulation. As we can see, when the selector is 0, after the reset the assert and the post edge, the output will increment by 2, which is in 1, 2, 4, 6. Until it's greater than 5, which is 6 now, the selector we will change it to 1 based on the testbench that we created just now. Then the counter will increment by in1 plus in2, which is 5. For better view, we change the radius to decimal. Okay, and 6 plus 5 is 11. Yeah, so it will increment by 5 to 11 and 16. Now the 16 is greater than 15, then we select 2 as the next our counter variables. So 2 is now 3, so we increment by 3. So 16 by 3 is 19, 22, and until 25. And when it's exceeding 25, it will stop the simulation. So this means that the M1 module is correctly designed. Next is the simple 8-bit register, which having a reset signal and enable signal to load the D to Q. And very simple, testbench is also created by setting D to different values, and we enable the enable to make it to make the output Q to load with the input D value. Let's simulate the modules. And we can see when the enable is inserted, the Q output will load with the value D. Also, when we change the value D at next post edge clock, the Q will load with the D value, updated D value. Next is the left shift 8-bit register. For this register, you have two enable signal. One enable signal is enable and also lock shift signal. When both of the signal is exerted, the Q will load with the initial value. While only enable signal is exerted, the Q will do left shift by inserting the SI signal to the LSB. This means the whole Q will be left shift by 1 bit. And the SO will display the MSB bit of the shifted Q. Next, for the testbench is created to verify the left shift 8-bit register. Initially, we will set the D to all ones as the initial case. The SI is equal to 0. When we start the operation, we will do a initialization by both enable and lock shift signal to 1. Then the Q will expect to load the initial D value. Then we deassert the lock shift 0 equal to 0. Then it will start shift left by 1 bit each of the clock period. And we wait until Q is equal to 0 because it's shift left by 1 bit with the value 0. So after a couple of clocks, the Q output will become 0. Let's run the simulation. Let's generate this finally. As you can see, when both enable and lock shift signal is exerted, the Q will load with initial value, which is all ones. And after the lock shift, signal, it will start to left shift by 1 bit each of the clock period, and will left shift by value 0, and until after some of the clock periods, the Q will become all zeros. While the SO will print out your MSB bit, most significant bit of the Q. And when all zeros, the SO will become 0. This means that the left shift AP register is correctly designed. That is the similar shift register, but we have doing it opposite direction, which right shift at 4-bit register. Also, it have a enable and lock shift signal, which do the similar behavior like the shift register, left shift register. And the SI now for the right shift, it will inserted at the MSB instead of LSB. And the SO will print out the LSB instead of MSB in left shift register. Also the same, we set the initial value in the testbench is all ones, and we do the same sequence by enabling both enable signal and lock shift signal. Then we deassert the lock shift signal and wait until Q equals 0. Now let's run the simulation. And you can see when both enable lock shift signal is asserted, Q is loaded with all ones, and then the SI loaded after the lock shift deassert and at the MSB and 111, 11, and 1 until 0. This means that the right shift is correctly done, and also the SO will print out your USB bit. When all 0, the SO will become 0. This means the right shift is behaviorally correct. And lastly, we will design a data unit by integrating the 3 registers that we discussed just now together and some arithmetic operation to realize the behavior of the data unit. And here the enable signal will be connect to a load signal, while the load shift signal will be connect to control signal. And from the attachment, we'll set each case of the control signals and load signals, and we wait until Z is equal to 1, which means the right shift, the output of the right shift becomes 0. And we run the simulation. Okay, here for the test band, we set the data A, the input, and data B to 100 and 111 respectively. And when we start the operation, we load the initial value of data A and data B to the internal A and internal B by asserting control A and control B, and also load A and load B together. And the internal A and B will become 100 and 111. Then we start our operation by right shift the data B and left shift the data A. And we check the LSB of the data B, whether it is 1. If it is 1, we left shift the data A, while if it's 0, we do nothing at the data A. And the data A will add with the P value from the last iteration, and we float it once the result at the P output. For example, for the first case, we can check the LSB of the data B, the internal B, which is 1. Then we add data A with the previous value of P, which is 0, and we can get 100 at the output P. Then we right shift the data B by 1 bit, which will become 11. And the LSB is now still 1, which means the data A will be left shift by 1 bit, which is 1000. Then the 1000 will add with 100, become 1100. And for the next step, the data B will right shift once more, and we will get the shifter value is 1. And data A will be left shift again, since the data B LSB is also 1. So the result will be 11100. Then for this case, we right shift again for the data B, and the data B will become 0. When the data B is 0, we will insert the Z signal, which means that our operation is done because we have no value inside the data B, and there is no further shifting will be done. inside the data unit module. So the result will be 11100. Then we stop the simulation when we see the j is equal to 1. This means that the data unit is correctly designed by using the shift register and also the register, and the P shows the expected value. I think that's all from my demonstration on the MC13 project. Thank you for watching.